Assalamu alaikum everyone, and today we'll be talking about summation notation, factorials, and a little fresh up about sequences. So we know a lot about sequences, right? There are many types of sequences. Sequences include arithmetic sequences, sequences that add, like a's of n is equals to n. Here we're seeing how the set of all natural numbers, like 1, 2, 3, by adding 1, which is why it's arithmetic. There's also geometric sequences, sequences that don't go around the arithmetic area. Instead, they square or involve exponents, like this one. And there are also sequences with no difference pattern, essentially. It can go anywhere it wants. There are also recursion formulas where the next term is defined by its previous terms, and the most famous of which is the Fibonacci sequence. Here, as you can see, after 0 and 1, the next element is just an addition of the previous two elements. So 0 plus 1 is 1, 1 plus 1 is 2, or 1 plus 2 is 3, and it continues on like that. There's another type of sequence that does this, and to do that we have to look at factorials. So what is a factorial? A factorial is basically multiplying a number by a number minus 1, by another number minus 2, all the way until the multiples go to 1. And here are some of the factorials. 0 factorial is 1. We'll go over that later. It's a little tricky, but yeah. 1 factorial is 1. 2 factorial is 2. 3 factorial, here's where we get to the tricky part, is 3 times 2 times 1, so it's 6, etc., etc., etc. One thing to note is that factorials work a lot like exponents, in which case they are operating on the number right beside it. So those are the factorials. Now, what can we do with these factorials? You know, they're all really cool and stuff, but how can we use it? If you look at this function and work it out, we get the first element to be 3, the second element to be negative 6, and the third element to be negative 1/4. Here the numbers are going to the negatives because as n increases, so does the subtraction, so the denominator becomes negative, and slowly going to 1/4 because as this increases, the factorial is also a factor here. So we're done with factorials and sequences, but there's one more to finish this huge algebra series, and that is summation notation or sigma notation. So what is sigma notation or summation notation? It is basically a short way to express a sum of a given things, and it's written with capital sigma, as sigma is a Greek letter that is the closest we have to S for sum. And this is an example of sigma notation. Here we have n is equals to 1. This means the starting number for n, and this is called the lower limit of summation, and on top we are writing any number of how many times we will be adding up. So this is the upper limit of summation. And we have here 2n squared. So we are going to be adding this number of times, and we work out the addition, and that will be the answer to the sum. We know how to express sigma notation as sums, but how to express sums as sigma notation? Here, let's take a look at an example. We have these numbers, and if you've been practicing math a lot, that these are perfect squares. So expressing a sum here is easy. We just write the sigma symbol. The starting number is 1, as we can see here. And on top, we write infinity because we're adding all the sums. And we write k squared here because k is the starting term. This is 1/2 plus 2/3 plus 3/4. And this can be expressed as the sum of u over u plus 1 infinity times, where the starting number is 1. As we can see, u at the start is 1. But it's not always so simple. Let's take a look at this sum. And another example can be 4 over 7 plus 8 over 8 plus 12 over 9 plus 16 over 10. This is a hard one, but if you look at the pattern a little, it's the sum infinity times, with the starting number being 1, of 4n over n plus 6. So that's it. We're done with all the principles we need to learn for this algebra series. But how do we make sense of what we've learned? Let's derive one of the key numbers of this algebra series, e. So we discussed in one of our previous videos that e is equals to 2.71828, and it can be used as the natural log of something. But how did we get here? This is Euler's number. Did Euler just sit around one day, make a bunch of random digits and make a number out of it? No. E is actually a sum. It's a sum of 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial, going on and on forever. This is an infinite series that gives a finite sum, which is e. Here, if you were to look at the first few numbers, you would see, after adding them up, that you've got e to a few decimals. This brings us to a part of calculus, which will inshallah be our next series. Calculus is about limits. It's at the heart of calculus. And limits can be expressed here. If you can see the sum, we express this as a sum. So after expressing it as a sum, as n approaches infinity, this sum approaches e. And here's this cool notation. Limit of n approaches infinity, the sum approaches e. So that was a lot. And that was the end of our algebra series. Next video, we're going to be finishing off our trigonometry series, and hopefully we can look into physics. So stay tuned for that. And that's all there is to it. Thank you for watching. If you have spotted any mistakes in my videos, you can inform me on that. Please like the video and share it to anyone that might need it. And thank you for watching, and I will see you next time. Bye.